Okay, so last time we derived this expression for the least squares solution for the prediction coefficients. But then we said that this is not very interpretable in the sense that you have a matrix A that contains both the feature values as well as these ones, and it is involved in sort of a complicated way to get the betas. And so we're going to come up with a different expression that is based on a derivation where we separate the intercept term, the beta 0, from all the other terms, beta 1 through d, which are the slope coefficients. And so the beta 1 through d vector is just the column vector going from beta 1 through beta d. And then this is going to allow us to come up with a new expression that is written in terms of the sample statistics of the data, the training data we're working with. And so to start with this, we need to understand what are these sample statistics, how are they defined and notated. So we started with some basic ideas of scalar variables. So since our targets are just scalar variables, if you have n targets y1 through yn, and you just average that list of numbers, you get what's called the sample mean, which we will denote by y bar. And that's the same average that you've seen many times in your lives. And you can do the same thing with the features. So here we're looking at the jth feature, and the indexes overall are different training examples of the jth feature. And so now we're doing an average over those indices I, and then we get the average of the jth training feature, the sample mean. And then we said the next more complicated statistic would be the variance, which is how much a quantity deviates around its mean. And in particular, you measure this by looking at the average of the squared deviation. And so when we're talking about the targets, we look at the yi's minus their sample mean, and we square that, and we average over all the i's, and we get sample variance, which there's actually a couple different ways to notate this. So one way is sy squared, and then writing it that way, sy without the square is known as the sample standard deviation. We'll see that there's actually another way to write it based on this expression in just a moment. So that would be if you look at the sample variance of the targets. Now you could also look at the sample variance of the jth feature. So here you take all the examples of the jth feature, subtract the jth sample mean, and then look at this average squared value of that, and you get s sub xj squared. And then one final thing is, so here we're looking at the targets on their own, here we're looking at the features on their own, but what's really key to prediction is how the targets and features relate to each other, because we're trying to predict the target using the feature. So that brings us to the sample covariance, which has a very similar structure to this, except rather than using y twice or x twice, you use y once and x once. And that's the sample covariance, and that is denoted as s sub xjy, because we're looking, and by the way, we could swap the order of these two. It doesn't matter because they're scalars. They're real numbers, so you can swap them, and that's why you might notice a discrepancy. Xj comes before y here, but either way it's the same. And so here, this is basically the simplest statistical description of the interaction between the targets and the jth feature. Okay, now based on this, let's see, is Xiaoqi Lu here? Yes. So based on this idea, can you see another way that we could denote this quantity besides sy squared? Can we just put y here and then change this notation? You see that? So, okay, this is what I mean. you could also write this as S sub yy. And if you write it that way instead of sy squared, what you're doing is you're using this sample covariance notation, but you're basically putting in y here and y there. Because if I have y there and y there, that's the same thing as y squared, right?
Yeah.
And so that's why I could write y, and I get the same exact thing as this, right? So sometimes when writing the sample variance, we'll actually write SYY instead of SY squared. It's the same thing, and we're sort of using this more general definition here. I just want to explain that there's different ways you might see this written. Okay, great. Any questions so far? Excellent. So now we're going to repeat those same ideas, except we're going to use vector quantities, because when we do our predictions here, we actually have not only just one feature, but we might have up to D features. And the way that we described the data set, if you remember, is we had a big matrix X, and then along the rows, we had n different examples of the feature vector of dimension D. And these guys, here they're rows, because they're transposed, are what I'm talking about over here. So what I'm saying now is, let's look at the sample mean of the entire vector xi. And now when you do this, you will get another vector, which we'll call x bar. But these are bold, and that's why we know they're vectors. So is this idea making sense? It's like we're doing something conceptually the same as here, but we're plugging in a whole vector and averaging a whole vector rather than just a scalar. Okay, so now let's say we do that, and let's say I look inside that vector. What will the first element be here? What will this be? Let me ask Alex Potarek. All right, yeah.
Could that, the sum of all the xi for that j?
Yeah, so we're looking at the very first feature, j equals 1, and we're basically looking at not only the sum, but also the average, right? And do we have a name for that quantity? Yes, do we have a symbol notation for it? X bar, right? But is it boldface or not boldface?
It would be not boldface.
Right, and will it have a subscript? Meaning, am I looking at a particular feature now? Yes, we're looking at the first one, right? So at the end of the day, the thing I'm talking about here is X bar 1, but this is a scalar. And then the next one is going to be X bar 2 and so on, all the way to the end, it's X bar D. So my point is when you look inside this vector average, you find the scalar averages that we defined on the previous page. Okay, so the jth term of X bar vector is the sample mean of the jth feature, which we call X bar J, no bold. Okay, is that pretty clear? All right, let's do something a little bit more complicated. Let's look at the sample autocovariance matrix. So this is going to be an entire matrix, boldface, capital letter, and this is formed by an average outer product. So remember that the outer product is a column times a row vector, and when I do that multiplication, I get an entire matrix, right? And that's essentially what we're saying. We're bringing the notation of variance into the vector domain, and I get an entire matrix called the autocovariance matrix. And when we look inside this, what do you think happens if I look inside the top left entry here? Think about, based on these and matrix multiplication, what is that entry going to be? Let me ask this to Yang Shen. So first of all, Okay, what is the first element here?
X1 minus X pi.
X1 bar, right?
Yeah,
And then if I'm talking about this matrix entry, I'm actually looking at the first one in both. And so I have the same quantity
so just
repeated, squared. And what is the name we have or notation we have for that entry now? Based on the previous page. I'm looking at a scalar. I'm looking at its squared deviation, averaging over all the examples.
X.
That's the variance, right?
Yeah.
Yeah, so this is the variance, in particular sx1 squared, or we could write it another way, sx1 x1 if we wanted to. Okay, so this is my point with the first bullet. The jth diagonal term is the sample variance of the jth feature. So here that the first diagonal term is a sample variance of the first feature. But if you look at other elements along the diagonal, the same thing happens. Okay, so when we look inside this matrix, we have variances along the diagonal. What about the off diagonal? We don't have variances anymore because what we're looking at is we're looking at the deviation of, one, let's say x1, and it's the deviation of x1 from its mean, and then maybe we're looking here at the deviation of x5 from its mean, and we're looking at the average product. So that is going to be a covariance. In particular, if we look at the jth row and kth column of this, we get the covariance between xj and xk, this being the thing we defined on the previous page. Okay, so when you look at the diagonal terms, they are variances. When you look at the off-diagonal terms, they are covariances of different features and each other. So this way, when you look at the off-diagonals, you can see, are my features correlated with each other, or are they independent of each other? If all your features are statistically independent, this matrix will look, it will be almost perfectly diagonal. It's probably never going to be exactly diagonal because these are just samples. If you have samples of statistically independent random variables and you look at their mean or their variance, covariance, it's not going to be the perfect statistics you expect. It's just going to be close to them. We'll talk more about the true statistics, random variables and stuff in the next unit. Okay, so anyway, what we've done now is, so we have the sample mean vector, x bar, we have the sample autocovariance matrix, which is basically like the extension of variance to a vector of features. But here we're looking at, only the features alone, only the features alone. We also want to look at the correlation, or really covariance, between the features and the targets. And that's what we have down here. You have something of this structure, but rather than features and features, you have features and targets. It's similar to what we did on the previous page, except now instead of a scalar jth feature, we have all the features together, this entire vector. Okay. So this is going to be a column vector. This on the right is going to be a scalar, and when you do that multiplication, you get another column vector. So this thing is going to be a column vector. And we call it SXY because it involves all the features X, and in this case, just our scalar target Y. Okay, called the sample cross covariance vector. So finally, let's take a look at this. If I look in the first entry here, what do we expect to see? So let me ask Thomas Wu. Yes. What do you think, what do we get if we look at this first entry into this vector?
It's probably S subscript XY.
Okay, so you're saying S subscript XY?
Sorry, X1Y.
Exactly. Here we're looking at the first feature and its covariance with the target. So that's what's in the first element here. And when you look at the jth element here, it's XJY. And that's what we're saying here. The jth term is the covariance xj. Okay, good. Sounds like you guys are catching on. Are there any questions on what we've done here? Okay, excellent. Let's move on. And there's another way of writing the autocovariance and cross covariance that is very useful. It shows up a lot in derivations. And so let me just show that to you here. So this is the definition we had from the previous page, the way we defined autocovariance. And I think conceptually this is the one that makes sense. It's like a deviation times a deviation. Another thing you can do, though, is you could expand this product into first times first plus second times first plus first times second times, or plus second times second. So that's what we have 4 terms. And so here's just our average of the first times first. That's what we have here. And then here we have the average of the second and the first. But notice what I did. I pulled out the x bar from the average because the average is over I, and x bar has no I dependence. So I can pull it out. And that helps me step back and realize, maybe interpret what this term is here. Does anybody recognize what this is?
Just the average?
That's right. It's a sample mean, and we call that x bar, but this is a boldface. So I'm going to put an underline under there because it's easier than trying to make it bold when I'm writing by hand. Okay? The same thing happens in the third term. It's this times this, but I can kind of imagine this average operating just on the xi and giving me another x bar. And now when you step back and look at it, you see that you have actually 3 terms. This is a minus x bar. Oh, sorry, I forgot there's a transpose. Well, no, here's the transpose. Okay, so overall we have x bar times x bar transpose. And then here we have x bar transpose. The first 2 are negative, and we have the same thing again but positive. So basically, this one and this one cancel, leaving 1 over n, sum I from 1 to n, x bar I transpose, that quantity minus x bar transpose. Forgot the bars. All right. I forgot to explain one thing. What happened to the average when I did this last term? Why is there no summation over here? Let me ask this to Zhiheng Tan. So why don't I need to write 1 over n, sum over I going to n in front of this term here? That's right, because essentially what I'm doing is if I look at this quantity, it's like I would just be adding up x times x bar transpose n times and dividing by n. And so it's like I'm averaging a fixed thing, and the average plays no role, so I don't have to include it. Okay, so here's the alternate expression for the covariance. You can either do an average of the squared deviation, or you can do an average of the, not the deviation, but the whole thing, the squared, minus the product of the means. Okay. So this thing often shows up in derivations, and it's good to recognize once you see that, oh, that's just the autocovariance. It's a lot of work to kind of go back from here back to this to try to realize that it's autocovariance. Okay. Any questions on what we've done here? Okay, now we can do exactly the same thing to the cross covariance. We just do xi times yi, first term, x bar times yi, second term, so on, so on. It's basically the same. So over here we have y bar. We recognize that as the scalar average of the yi's. And over here we have vector x bar. And then finally, we notice that this term cancels this term. So cancel, and what we have left is this average over I of xi times yi. So here, it's not the deviation, but just the raw average of the product. And then here, x bar y. Okay, so these are going to be useful today if we get to it. I don't know if we will. Probably not, but they're useful when we come back to it next lecture. Okay, any questions so far? Okay, great. So now we can dive into the derivation. So this is the RSS. We've seen this several times before. The only difference is now when we write the prediction, so this is the prediction yi hat, we are separating out the offset or the intercept minus beta 0. Sorry, let me be a little more precise. This is minus yi hat. We're separating out the intercept from the slope terms. And so now, let's see where I want to go with this. Okay, so what we can do is we can just apply the chain rule. So it's something similar to what we did last time. So we want to do, we can move this derivative through the sum and then focus on differentiating this and summing it. To differentiate this, using the chain rule, we're going to have 2 times this whole thing. So let me write that. 2 times the sum of this whole thing, which is going to be yi minus beta 0 minus vector xi transpose times vector beta 1 through d. We're going to have that, and then we have to finish the chain rule times the derivative of the inside with respect to beta naught. So as for that derivative, let me ask Chris Gao, what would that derivative be? The derivative of the inside of this with respect to beta naught?
So it's minus y.
Minus 1, that's it. So we put a minus here for the minus 1, and we're done. So we have now the derivative of the RSS with respect to beta 0. That's this expression here. Okay, we'll work on that some more, but let's also look at the derivative of the RSS with respect to beta j. So for here, it's again the same expression, except remember how we like to do our calculus with respect to, well, here you can see we're taking a derivative with respect to one of the individual beta j's that is inside this vector. So to expose that, let's write this inner product back using a sum. And now I want to be careful not to use the variable j in my sum because I'm already using that for something else. So I'm just going to use j prime. And I have the sum. This is xi j prime times beta j, summing from j prime going from 1 to d. And so this is going to be useful now when I take the partial derivative. So once again, I do the chain rule, which is I'm going to have my sum. Then I'm going to do the chain rule, which is going to be 2, and that's going to show up over here. 2 times the inside, which is the same thing as above. And then finally, we have the derivative of this with respect to beta j. So let's see, is Sirach Gensch here? Yeah. So what's the derivative of this with respect to beta j? So most things can fall away, right? Because they're not dependent on beta j. So this is not dependent on beta j. This is not dependent on beta j. When I look at this sum, how many of these terms are dependent on beta j? J being some fixed number. Okay, so we're taking, so we said these things don't involve in the derivative. Now, let's say I take the derivative of this with respect to beta j. What's that going to be?
Negative xij.
Yes, exactly. We have a negative xij. So over here, we're going to have our negative, and over here, we're going to have our xij. Okay, so we can resume with this derivation next time, but I think now we should prepare for the midterm. So if you don't mind, please put away everything except your pencil, what you're going to write with. Put your phones away in your pockets or your bags. And also,